That was a little Lady Madonna by the Beatles, a little arrangement that I put together one time. All right, we're going to do the calculator part of our test review for the online trigonometry class. And the first thing we're going to look at is some of the first things we learned this semester, and I'll display this calculator to demonstrate this. So to begin with, what we want to look at is how you would do something like this, problem number 1. And I'm going to show you how to, a couple of ways to do this on the calculator on here. So the first thing that you could do is don't put the negative in. I always see students put this negative in here. So what you could do is you could go 29 plus 47 divided by 60, since there's 60 minutes in a degree, and then plus 29 over 3600, since there's 3600 seconds in a degree. Now, you can put it in just like this, but don't put the negative in because I'll show you what happens. That's a real common mistake. So you can put it in like this, and let me show you what happens on this if you do this. Okay, so you get this. The answer to this problem definitely would be, and I want you to round this maybe to 100th of a degree, so that would be 29.79 if you're rounding out to 2 decimals. Then you just tack the negative on like that, so that would be the solution of that problem then. Now notice if I did this, if I put the negative in, let me show you what happens. You do 29 plus 47 over 60 plus 29 over 3600. Okay, look what happens. Different answer, wrong answer. Okay, it's because that negative does not need to be a part of that calculation. Now, here's an alternative approach. If you want to do it this way, you can certainly put the negative in. Then you can go to second apps to get your degree symbol to come out. Then 47, back to second angle, apps, option 2. Okay, then you're going to put in the 29. Now you got to go alpha plus to get that to come out. Then that'll give the answer. So if you do it that way, you can put the negative in. So that's real important. Okay, so the next one is basically going to be done about the same way. So when we're doing this problem, either one of the two ways that I just showed you how to do that on the calculator would be sufficient. So it's totally up to you. I generally just do it like this. I find it just as easy to find the buttons that way, and it also kind of helps to a student reinforce the relationship between minutes and degrees and seconds. So this is the way I always do this. All right, so if I put this in, then we'll get a good answer, and then round that off to the 100th. So that is going to be about 218.97 degrees. Is what you get there. Okay, I need to put my degree symbol up there. Okay, so that's how you do that. Now, if you want to look at the next situation, moving up on this number 3, there's two ways that you can do this number 3. So one thing on this one, what you're doing is, first of all, the answer is going to have negative 72 degrees. But then when you're dealing with the point 14, you're doing backwards of what we just got through doing. So if we take 0.14 on the calculator, and if we multiply that by 60, you're going to get 8.4. Okay, and what that means is, first of all, the 8 becomes the minutes. Then you have a leftover 0.4, so you need to take that leftover 0.4 times 60 again. Hopefully you don't need a calculator to do that. That's just 24. So that would give 24 seconds like that then. and then that would be your solution to your problem, like that, okay? So you can do it like that. The other way that you're more than welcome to do this on a calculator is a calculator has what's called a DMS key, and what did I just do? Okay, there we go. All right, so what you can do is you can do this. So we can go negative 72.14, and then you can go second angle, and then go down option 4. And what that does is it converts it to degrees, minutes, and seconds for you, so it gets the same answer. So you're also more than welcome to do the problem that way. Okay? All right. So I get my pen back on here. Okay, so this one the same way. You could go 248 degrees, and then you can take the 0.56 times 60. You want to work that out. Okay, so when we do that, we'll have 33.6. Okay, so the 33, again, becomes the minutes. Then you got to do the leftover 0.6 times 60, sorry, which will give you 36. So that will give you the 36 seconds. And then that would be your solution to your problem. Okay? And again, you can also do that with that DMS key. You can go 248.56 and second apps to get the angle command to come up, get DMS to come up, and then you got the same answer. Okay, so take your pick in the way you want to do that then. Okay, moving on. Okay, number 5, what we're doing is we are converting this to Radian measure, okay? And on a calculator, you do this. So basically what you always do, if you want to convert degrees to radians, what you do is you multiply it by pi over 180. Okay, so you can put this in your calculator in one step like this, just using your pi key. So you go 115.2 times pi, and then divide by 180, and put it in like that. Okay, and then that'll give about, looks like I want to round this to 3 decimals, so that looks like it would be about actually 2.011. The zero's got to go up to 1 since the 6 is next to it. So that's how you do that. You're just multiplying by pi over 180. Okay, and these are intended to be problems that you just do in one step on your calculator. Okay, the next problem you do this way if you want to. You could just say, in parentheses, 27 plus 54 over 60 plus 29 over 3600. Close the parentheses. That way it converts that to decimal degrees. Then multiply by pi over 180. And you can go to the calculator like that. Okay, so 27 plus 54 out of 60 plus 29 out of 3600. Okay, notice, going to do that. Now you can do this in 2 steps. So you can take that, and then you can go times, then you can do the pi key over 180. I forgot to put my parentheses in, but it doesn't really matter. You can do that in 2 steps. So anyway, this thing rounds off then. If we're going to round this to 3 decimal places, that would be 0.487 would be the approximate answer of the problem. Okay. All right, so you can do that like that. You can also do this kind of calculation like this if you want to. You could go 27, second angle, get the degree symbol to come up, 54 minutes like this, 29 seconds, okay, like this. Oh, you got to go like this on the seconds. I always forget this. You got to go alpha like that. I don't know why it's there on the calculator. It's just the way it is. So you got times pi, and then you divide that by 180, and everything's all cool. All right, same answer, okay? All right, next thing, do this backwards. So if we're taking radians and we are multiplying this, change that to degrees, well, you do the opposite thing. So the opposite of multiplying by pi over 180, the opposite of multiplying is really dividing, okay? But when you divide, that's the same thing as multiplying by the reciprocal, so you do this. So what you're going to do is just take the 0.011 8021. Okay, we're going to multiply that by 180. Then divide that by the pi key like that. Just do that in one step. You don't really need the parentheses on that. So or you don't need the 0. So I'm going to go 0.8021 times 180. And divide by the pi key. Okay, like this. Okay, and then that will give this to you. Okay, now I say I want this changed to degrees. Like this. Hold on. Yeah, we're going radians to degrees like this. So you would have 45. If you wanted to round it to 2 decimals, then you would have 45.96 degrees. Now, another thing you could do on this if you wanted to is you could go through and you could go second angle DMS. If I wanted this in degree minute second form, then you can do that. And then what you would have is you could write that as 45 degrees, 57 minutes, and 25 seconds, okay? And that hopefully makes a lot of sense to you. Notice that there's 60 minutes in 1 degree. So notice that was real, that 0.96 is real close to 1. So you could have either of these two answers on this problem. And it's always good to, when you get an answer, to estimate. And that's how you catch any mistakes you make when you erroneously enter something on the calculator. Okay, moving on. Okay, the other thing we learned, basically, was how to find the length of an arc. Now, the thing that we basically learned on this, I believe, we went through was if you have any type of a circle, you can find the length of the arc pretty easily if you know the radius and you know the central angle. So, you know, that would be, of course, a radius like that. And then if we say we formed some sort of a central angle like this, before I do this problem, I just want to remind you what the formula we learned is doing. Okay. So what you'd have is if, say for instance, that you knew that this angle was, you know, something, theta, then of course this is the radius, and what the arc length is, again, is that piece right there. So what we learned is we learned the formula S equals R theta, okay? Regardless of what the angle is, I think the textbook that we tend to use says alpha times R. It's all the same. It's just multiplying an angle by the radius. Now, the thing that's real important on this problem is your angle must be in radians, because if it isn't, you'll get crazy answers. I mean, like just total nonsense answers. So the thing on this one is, that is in radians, okay? It doesn't have a degree symbol on it, so it's in radians. So really all you got to do is just go S equals alpha, which is 9 pi over 5. And then you're going to multiply that by the radius, which is 0.934 millimeters. And then you can just round that off in your calculator like this. So you can go like this. You can go, if you want to, you could go 9 pi over 180. Okay, now if you put that in parentheses, what that's, not 180. Let me back up on that. Okay, let's see, how do I backspace on this? Okay, I'm going to go like that, over 5. Then I'm going to close the parenthesis. And what that does, see, is that just changes that to a decimal. Now you can put in the 0.934. Okay, then we'll round that off. I think the problem does not really say how to round off, so it doesn't matter. So let's just round this maybe to 2 decimals. So that would be about 5.28 millimeters. So that would be the length of the arc. The key thing on that when you're doing that is to make sure that you're in radian measure. Okay, let's see what this next problem has going down here. All right, this says city park. We got a baseball, distance from home plate to third base. Let's see, we have 80 feet there. Angle between the outer edge and third base lines is 90 degrees, of course. Let's see, the radius 250. Now let's see, we're going to find the area of the outfield. This is not drawn very well. That didn't come out on my handout very good. Because, I mean, technically, what they're saying is this is going to be an arc of a circle. You know, that's the idea. So it doesn't look like an arc of a circle, but that's technically what they're saying on this. So what we need to do on this is we're finding the angle between the outer edge of the first and third bases. Okay, so here's first base, and here's third base. And what they're wanting to do is find the area on the outer edge of the first and third bases. Okay, so here, this is what they're talking about here, basically, is we want to look at, okay, this piece right here, and then we're going to look at really this shaded region right here. So we're talking not about the whole thing, but we're talking about this little kind of piece in here, like that. So it's really a part of an arc, so you have to put together a mathematical expression that would represent that area then. Okay, so that's what we're basically going to be going through and looking at, is this area right here that we're going to call A. So the way that I would look at this is, we know the formula for an area of a sector is 1/2 alpha r squared, typically is the way the textbook writes out. So we'd have to do this. We'd have to first of all do the area of the sector. All right, and we know the formula for that. And then we'd have to subtract the area of the square, the diamond. A diamond is a square, okay? All right, so we got the area of the square, all right? So you have to do those two things together like that to get that leftover area. So it's the big area, the sector, minus the little area, the square, gives the leftover area. Okay, one thing that you got to do on this that's important is, notice they gave you that you have of course, a 90-degree angle. So that alpha is 90 degrees, but you absolutely have to convert that to radians. So that's going to be 90 pi over 180. So that reduces down to pi over 2. Okay, so when we do this, the area of the sector is going to be 1/2 times the radian measure of the angle, pi over 2 radians, times the radius. Now that radius is this thing that they gave you. That is 255 feet to the second power. So we're going to work that out. Now the area of a square is just base times height. Okay, so this is going to be 80 there, 80 there. So that's going to be 80 feet times 80 feet. Length times width, or you can think of it as just multiplying that one side by itself. Okay, so now if we go through and put this together, let's go ahead and just write this as pi over 4 times 255 feet squared. And then we can multiply that out. That's going to be 1,600 square feet like that. Then we can go to the calculator to finish this up. And you can do this pretty much in one step on this calculator. So let's see. I'm going to go ahead and just take pi divided by 4. Then I'm going to multiply that by 255 to the second power. And then that'll give you the area of the sector, which is 51,070.5 feet squared. Then we'll subtract off the smaller area, the 1,600 square feet, to get the leftover area. Okay, so let's put that in, 51,070.50 minus 1,600, and then that will give the leftover area. Okay, all right, so that gives about 49,470.5 square feet. So that's a really nice problem that takes a couple of steps to work out. All right, I just found an arithmetic mistake, so let's be a little cautious when we're doing these problems, okay? And I know better than this, okay? I can do all these problems. I can do everything sometimes except press numbers right on my calculator. My error was here. If you're following along, you may have noticed that. Okay, that is actually 6,400 feet. Okay, so let's get that corrected then, so that we get a correct answer. So let me erase that. And let's do this the right way, teacher. And see, I record these videos on YouTube. How incredibly embarrassing of me. All right, hey, we all do the same thing. It's okay to see your teacher make mistakes like that. Okay, so let's go ahead and let's get that corrected, get the answer, then we'll move on here. Come on, behave thing. Do what you're supposed to do. There we go. Okay. All right, so let's get that corrected. This is going to be 64,000 square feet. Okay, now I can go to the calculator and then I can now finish this up. So I've got 51,070.5 and then minus the 64,000. I thought that sounded off a little bit on that. So that is, now that's really bad. Okay, if I got that. Now I notice I must have put something totally wrong in there. Okay, now I'm really embarrassed by what I'm doing. I put an extra 0 in there. Okay, this is really good stuff. Of course, I'm doing this recording at like 6 in the morning. That's going to be my excuse for today. All right. So 6,400 is what that should be. But, you know, there's always a learning thing of making mistakes. I mean, obviously, I got a negative area. Now, sometimes I see students get things like that, and then they don't catch their error. So you always want to be thinking about your error. That's generally how I catch what I make, is answers just don't make sense. I've got pretty good estimation skills, and you always want to basically be doing the same thing. So we have 51,070.5, and then we're going to subtract off the 6,400, and that'll give the answer. Okay, so it looks like that will give 44,670.5 square feet. So finally, I think I deserve a round of applause for all the headaches going through that problem. All right, very good. So that should be the official answer of the problem. All right, so let's see. Now we're going to go on, and I'll move up to this next thing. And what you're doing with this one, really, is this problem says, find the radius of a circle that has a central angle intercepting an arc of length S. Okay, so what we're going to do is, really, this is an application, again, of this formula. So we have S equals alpha times R. So if I want to find the radius, I can go ahead right now, and I can divide both sides by alpha. Of course, that will cross out that value of 1 there, so we'll end up getting R is equal to the ratio of S over alpha. Okay, so let's move over here and let's get that put together. Now again, the S is 15 inches. Okay, and you're in radians, so that's real important. If you're in radians, you don't have to worry about a conversion, so we just do 2.5 radians, and then we can round off that answer. So we'd end up having 15 divided by 2.5. Okay, like that, and then that would be equal to 6. Okay, so we got 6 inches. One thing I want to mention on this too is radians. We don't say inch per radians. Radians is really not a measurement. It's really a real number, and it's almost like a placeholder that we use to represent that is the type of measurement that we are in the angular system. So when you're dealing with radians, it's really not a unit. So the answer is just in inches. Okay. Okay, here's an area of sector problem. So we did one of those a few minutes ago. So you have area equals 1/2 alpha r to the second. Okay, so we're going to take 1/2 again. We've got to make sure that's in radians. That is in radians because there's not a degree symbol. If I was real sneaky and put a degree symbol there on pi over 2, then you'd be in radians, or you'd be in degrees, so be careful. All right, so we just bring that down. That's pi over 2. The radius was 10, so we're going to take 10 centimeters, and we're going to square this. All right, I recommend that you just multiply everything out as much as you can before you go to your calculator. So that's pi over 4 when you multiply that out, and then that would be 100 square centimeters. Okay, so that is going to be 100 pi over 4 square centimeters. Well, that's actually going to be 25 pi centimeters squared. Now, that is the precise answer to the problem. Of course, if you went to the calculator and if you did this, what you would do is you just go 25 and then you multiply that by the pi key, and then that'll give you this answer, so you could round that off if you wanted to. And we'll just say that's about 78.5 square centimeters. So there's an exact answer to these problems, and then there's a approximate answer, so you want to kind of pay attention to what you're being asked for. Okay, so that's how that goes. All right, now this next problem is one that tends to be kind of a doozy for students sometimes. These angular velocity, linear velocity problems tend to be a little challenging for students, mostly because of the physics that's going on in it. It's an application. It tests your understanding of certain concepts, so that's kind of the key thing to get down. So let's see. This one right here says you have a pulley, and it's rotating 15 times in 15 seconds. So the way I look at this problem is kind of like this. You've got some sort of a circular pulley here, and what's happened is generally you use a pulley, of course, to represent or to make work easier. So what we're going to typically do is have some sort of a cord that we pull on. That's not very good. Then we have some sort of a weight that we're lifting like a buck. Sorry about that. That's pretty sloppy, but you get the point. All right. And the thing on this is it says you have a radius of 7 centimeters. And of course this thing is turning, so it's turning circular like this. Now, the thing on this is, if you're doing this now, and this pulley could be used for something else, by the way. It doesn't have to be used to lift a weight. So if it's rotating over and over and over again, it's obviously doing maybe some other kind of job. So what we're going to look at here is the key thing on this to me is, what did I give you? Well, it's pretty clear I gave you a radius. But the other thing I said is it does 15 revolutions in 128 seconds. So what that would mean then is that's really an angular velocity. An angular velocity can be thought of as the amount of radians you go through in a unit of time, but you can also think of it as how many revolutions you go by in a unit of time. So we could say 15 revolutions in 128 seconds, like that. Now, we generally want to change this to radians per unit of time. So one of the things we learned is every time there's one revolution in a circle, we know that is 2 pi radians. Okay, so we're going to get that worked out. So what we're going to go ahead and do now is let's just go ahead and do that on the calculator now. So when I do that, I'm going to just go straight across. Okay, you can kind of watch how I'm doing this. So if you want to. So we got 30 pi. Notice the revolutions cross out. So you have 30 pi radians per 128 seconds. Okay, so now we can go to the calculator and get that put in. So I'm going to go 30 pi divided by 128. And that's going to give about 0.736, let's just round that off like that, radians per second. Okay, now you want to find the angular velocity, that's it. Okay, so, and the angular velocity, notice on this you might be asking, well, what did the radius have to do with it? The radius has nothing to do with it, okay? The angular velocity is actually totally independent of the radius. Doesn't make any difference. So that should be the solution to the problem then. Okay, so let's move on to the next thing here. And let's see what number 13 has going on it here. All right, this says you have a wheel that's rotating at 3 radians per second. Now see right there, just stopping right there, that tells you that you have an angular velocity. And that's one of the things that I stress when I teach this is you got to know what you're given. How did I know that's an angular velocity? Because of the units. It's in radians per second. Okay. Then you have a wheel that has an 80-inch diameter, so you're going to find the linear velocity. Okay, and you're going to find that in feet per minute. Okay. Well, first of all, what you really have on here is there's a real simple formula that connects those two things. So angular and linear velocity. So what you got going on here is it says that you have a diameter of the circle, and the diameter of that circle, of course, goes through the center, and it says that is 80 inches. Okay, and this thing is rotating, so it's rotating some way. But the connection is that the linear velocity is equal to the radius times the angular velocity. So that's one formula we learned. Well, the radius is half the diameter. So if you cut that in half, see, I'm thinking ahead there. 80 divided by 2 is 40 inches, okay? So we're going to take the 40-inch radius, and you're going to multiply it by the angular velocity, like that, and then you're done. Okay, so that would mean the linear velocity would be 120 inches per second. Now again, one of the things I want to stress is radians is not really a unit. So right now you're in inches per second. So now what you want to do is a couple of conversions. And when we do conversions on this, the idea is if we want to go feet per minute, which is what the problem is stating here, one thing we want to do is we want the inches to go away. So I'm going to put it in the right place to make them go away. And we know that there's 12 inches in 1 foot. So that takes care of getting us in feet now. Okay, now I need to convert the seconds to minutes. So again, the seconds needs to be on top so it will cancel. So we're going to have, we're going to end up with 1 minute makes up 60 seconds. And then we can go to our calculator and crunch out the answer then. Okay. All right, now there's a couple of things that you can do on this if you happen to notice it. What I notice on this is, and maybe you do too, is 120 divided by 12 is 10. So now I don't really need to go to my calculator. If I just take 10 times 60, I get 600. And notice that now my answer is in feet per minute. So I've done the necessary conversion on that problem. Then that would be the solution of the problem, like that. Okay? So you got to know what you're given and what formulas get you there, primarily. Okay, now this next one has another thing with the pulley. This says the pulley has a diameter of 27 inches. It's driven by a belt, which is moving at 857 feet per minute. So we're going to find how many revolutions per minute are made in the pulley. Okay, now the thing that's key on this is a linear velocity. So v, the linear velocity, is given as 857 feet per minute. So the question is, how did I know that it's linear velocity? Well, it's because of the units. It's a distance over a time. That's what a linear velocity is. So feet per minute would be a valid unit measurement for linear velocity. Okay, well, one thing is, we also have a diameter on this of 27, and we got to change this to revolutions per minute. So that really means revolutions per minute is really a valid measurement unit-wise for angular velocity. So ultimately we've got to do that. The formula that we use that connects these two is this. Okay, so if we're going to find that angular velocity, we already know the linear velocity. So what we can do here is we could solve this equation for omega right now. So we would have omega equals V over R. Okay, so that's what we're going to end up using in this first step of the problem then. All right, so what I'm going to go through now is I'm going to have V is equal to, or I'm sorry, omega is equal to, because we've got to find the angular velocity. Right, so let's do that. So we've got the angular velocity here. And we're going to do V over R. So V is 857 feet per minute. And then we're going to divide that by the radius. Okay, well, the radius is 27 inches. So half of that, if you do 27 over 2, that will give you 13.5, I believe. So then we're going to crunch this out. And let's see, that was in inches. Now notice we're a little bit off on our units here. So one thing that we need to do is, see, this is in feet, this is in inches. So we kind of got a little issue that we need to address here at this stage of the problem. We need to just go ahead and address it now. So what I would recommend that we do is let's just go ahead here at the side. And let's do this, okay? Let's just take inches to feet, okay? Like this, so we know that we're going to convert that to feet. Inches need to cross out, and we know that there's 12 inches make up 1 foot. So that would end up being, if we do 13 divided by 12, that'll give about this amount. So that's going to be about 1.083. Come on, 1.083 with the 3's repeating. All right, so let's go back here now, and let's do 857 feet per minute. And then let's divide that by 1.083 feet, like that, since we now have done that conversion. Okay. Now, if we do that, now we're going to have what omega is. So I'm going to put this in like this. I'm going to go 857 divided by 1.083. Now, see, I just put a bunch of 3's in for accuracy. And then that'll give about 791. And let's just use 791.1. And then that is going to be in radians, per minute. Okay? So the radians are kind of a placeholder like I talked about. So you really got that now in radians per minute after the feet cross out. Okay, so now we're ready to convert this because the problem said we want this to be revolutions per minute. So if we're going to convert this to revolutions per minute, we need to do the dimensional analysis on this now. Okay, so here's how this is going to go. So we're going to take 791.1 radians per minute. We don't want radians, so what we're going to do in our unit conversion is we're going to do this. Okay, we're going to multiply that by, we know that there are 2 pi radians per 1 revolution. Okay, now just by doing that one step, what you've done now is you have your answer in revolutions per minute as you were asked for. Okay, so now we just need to go to calculator. Now watch how I do this in the calculator carefully. I see students mess up on this all the time. If you go 791.1 divided by 2 pi, okay, you may think all's good, problem's done. Well, you're wrong. You must do it this way. Okay, you have got to get the calculator to do the 2 pi before it divides. Okay, and that's the reason for that is the calculator is just following a computer program, and it's following order of operations. So it's doing multiplication and division left to right. So notice on this that what it did the first time is it did 791.1 divided by 2, got the answer, then multiplied by pi. That's not what we wanted it to do. We wanted it to do 79.1 divided by the whole expression, like that. So the correct answer to this problem is this. Okay, be careful about stuff like that. So you would end up having 125.9 revolutions per minute as your final answer to that problem. Okay, that's a great problem. Okay, now here's one more, I think, that has a little bit to do with velocity, and then we'll do some stuff on the calculator to kind of wrap this up. Okay, so this one, let's see, let's kind of look at what the scenario is. We have a satellite that's above the Earth, so I'll just take a couple of circles to represent things here. So let's say this is Earth. Okay, so here's planet Earth. And let's see, they gave you the radius of Earth. Okay, so they're given the radius of Earth as 3963 miles, so that's a given. And then above that, you have a satellite. I'm not going to draw this to scale, obviously, but let's say that is your satellite. And that satellite is rotating around the Earth. Okay, so our job on this is we're going to ultimately, they want you to find the linear velocity. And if they want you to find the linear velocity, what should come to mind pretty much immediately is r times omega. So let's see if they did indeed give you omega. I bet you anything they did. Let's take a look. Okay, they said it does one orbit every 83.42 minutes. So sure enough, they did. So what you're going to do is the angular velocity of the satellite. Okay, and this is the angular velocity of the satellite now. That's going to be given as 83.42, and it's orbits. Orbits is the same thing as revolutions. So it's doing that many revolutions per minute. Okay, So what we need to do is we need to go ahead and do a conversion on this to radians per minute. Okay, so we know that every time you have one revolution, you have 2 pi radians, like that. So we just need to go ahead and get that calculated out. So let's do that on the calculator. Let's take 83.42 multiplied by 2 times pi, and then that will give you about 524. Let's just round to 2 decimals, 1.4 radians per minute, like that. Okay. All right, now, the formula for finding the linear velocity of that satellite is going to be taking the radius times omega. Okay, so what we need to do is look at the radius. Now, you got to be careful about the radius, because it did say one other little piece of information, as it said that satellite was 879.4 miles above the Earth. So when you do this, you actually have to go like this. You have to go, the radius would be the grand total of these two things. So you'd have to take the radius of the Earth plus the height of the satellite when you put that together. Okay, so that's going to be on the calculator now. Let's take 524.14 and let's add, no, what am I doing? Come on, pay attention, Brad. 3963 plus 879.4. Okay, so we're going to get that grand total now. So that's going to be 4,842.4 miles. Okay, then we're going to multiply that by the angular velocity, which was 524.14 radians per minute. Okay, and our answer is going to be in miles per minute. Now, they don't say on this problem what units you want, so let's go ahead and crunch that out and see what we get. So I'm going to take the 4842.4, and I'm going to multiply that by the angular velocity. Okay, like this, and that's going to give this, that's a really, really big number, isn't it? Okay, well, that's because it's miles per minute, I guess. Okay, so let's go ahead and do this. We got 2538095.536, and see that radians is unitless, so that's really in miles per minute. Okay, now probably on this one it makes better sense to change this to miles per hour. So let's say we know that there are 60 minutes in an hour, so we could go through and then do that. Okay, so hang on just a minute. Okay, I paused because my answer was weird. It wasn't making any sense to me. So this is what you get into, and I hate to make mistakes. I make them. This is the second big one I've made here. Now, this is what I did not read right, and this is what you get into in these problems if you're not careful. It said one complete orbit every 83.42 minutes. Okay, now I didn't do a good job of that at all. So let's take a look and let me correct what I totally screwed up on that. Okay, so I'm going to erase all of this stuff right here and show you what the bonehead professor was thinking here. All right, so here's the idea. Okay, it says this. Okay, it says that you do one revolution every 83.42 minutes. Okay, not what I said. Okay, now we got to change this to radians per minute. Okay, so we know that every time that there is one revolution, we know that there are 2 pi radians. Okay, like that. Now we're going to get that correct. So it says one revolution for that. Sometimes you read something and you go through it too fast and you don't think carefully enough about the units, and that's where I screwed up on that one. So my apologies, it just happens. All right, so let's see. 2 pi divided by 83.42 is going to give me this value. Okay, so that's 0.075 radians per minute. All right, so now let's get this problem finished and let's see if we can get this put together a little bit better now. So let me erase some stuff as we go through this, and then we'll get this all taken care of. All right, so we got that. Let's make that correction now. So we now know that we've got 0.075 radians per minute. Okay, so now when we go down to where I screwed up, we need to do this. Let's take that out, okay, and let's replace that. Now let's get the final answer of the problem, and let's get this right this time. Get something sensible. You know, and it doesn't, sometimes it's good for students to see how somebody catches mistakes when they make them. I got this crazy answer that made no sense to me whatsoever, so I had to look at it, and that's what you get into sometimes. Nobody's perfect. We're all human beings. All right, so here's what we do now. We got the radius we said was these two things added together. So we have the radius of the Earth, and then we have the height of the satellite. Okay, and then what we're going to do is we're going to multiply that now by the correct thing. Okay, now we can get the answer. And we can just do this on one step on the calculator if we want to. We can just go parentheses, get the calculator to add the radius up for us. So 3963 plus 879.4, close parentheses, and then times 0.075. All right. All right, drum roll. Let's see if we get a good answer. Ah, so much better. So much better. All right. All right, I should have done it on my guitar, though. Okay, all right. So there we go. So your answer is going to be 363.18, and that's going to be in miles per minute. Okay? So miles per minute is what that should be. All right, so that's the answer. All right, sorry about that. Okay, so let's go on now. I think the rest of this is going to be just some calculator stuff. The stuff we do in with angular and linear velocity is a little challenging. It's good, though. Okay, if you're going to go on and take physics someday, physics is all about doing the math, but the harder part of physics is understanding the concepts, and based on the concepts, being able to do the math. All right, so let's see what we got going down on this problem here. So let's see, we're just going to do some calculations on this. Now, first of all, on number 16, the key thing on this is you want to be sure that you're in degree mode. So what we're going to do is I'm going to clear everything off, and if I go to my mode button, make sure that you're in degrees. If you aren't, you want to get that changed, okay? All right, now we can go ahead and just put this in. So we put cosine 36.9, like that, and then we get the answers. So we can round that off now. So that is 0.7997, okay, if you round that off. Okay, next problem, you are in radians. Okay, so you got to go to your mode button, change to radians. So you just get the cursor blinking on radians, then press enter. So now you're in radian mode. So now we want to press the cosine of 21 pi. Just use the pi key for accuracy. 21 pi divided by 8. Let the calculator do all the work for you. Okay, it's negative because of the quadrant we're in. If you have if the cosine turns out to be negative, it means you're in quadrant 2 or quadrant 3. So this is going to be negative point. I'll write that again. Negative 0.38, and that looks like that would be 27. 3827 if you rounded that off to 4 decimals. A lot of times we round these things to 4 decimals because back when I was a trig student in the last century, I think it was about 1982 or 83 when I was in my trig class, and we went to the back of the book and looked these things up. Okay, that's how old I am. All right, so let's see. Next problem, we got to go back to degree mode. Okay, so you got to be careful about this. So let's go to degree mode and go like this. Okay, there's 2 ways you can put this in. Kind of up to you. So one thing you can do is just press your sign. Then you can go 9 plus 30 out of 60. That's the way I do it. I just find it to be quicker. Okay, then we can round that off. So that's going to give 0.1650. Okay, like that. Of course, you can also do this like this. I would hope that you just know that's 9.5 degrees. 30 minutes is 0.5. Okay. The other way to do that would just be to put in your minutes and seconds. So you could go sine 9, second, angle, degree, 30 minutes. like that. Go down like that, put it in, same answer. Take your pick, whichever way you prefer. Okay, next one is degree mode. So you're going to go cosine, negative 437. It's a negative angle, so you're going clockwise. Ends up being a positive answer because you're probably either in quadrant 1 or quadrant 2. Believe that one puts you back in quadrant 1, it looks like. So that would be 0.22495. Now in this case, you need to take this whole thing up to 50, so that would be 0.2250. Like that is your answer to your problem. Alrighty, okay, let's see. Moving on here, let's see what else we got to do here that I wanted to look at. I guess a couple other applications that I wanted to take a look at. Okay, now this thing is just learning how to use what we call the inverse sign. And first of all, in this one, if you read the problem, it's saying that I want the answer to be rounded to the nearest tenth of a degree. So see, what you're doing on this is you're finding the angle. Okay, basically I'm giving you the value of the sine. The sine is a ratio of y over r on a circle, the y value to the radius. And so what you do on this is you type this in your calculator like this. You want to be in degree mode. You want to make sure of that because I'm asking for a degree answer. So now you go second sine to get the inverse sine out, and that's what that is doing, is it's finding the angle for you. So now you put in 0.5863,909, like that. And then that gives the answer. We can round that to the tenth of the degree, and that would give, basically, alpha is approximately 35.9 degrees, like that. Now notice what happens on this. If I was to go back and do now just the sine of 35.9, notice that I get back about the same answer. Okay, it's a little different because I rounded, of course, but the inverse sine is finding the value of an angle. Okay. All right, let's move on and do a few more of these things then. So this next problem to the side here, we're just going to go second cosine of 0.40997389, like that, and we'll get the answer of the problem. So just round that off to one decimal. So that looks like that's going to be 65.8 degrees, like that. Okay, all right, moving on. Next one, you want to go like this. You want to go inverse tangent of 2.0404315. Whoops, I totally missed my decimal, didn't I? I didn't do that right at all. So let's go inverse tangent, get that out. 2.0404315, like that. Okay, and that'll be about 90 degrees. Okay, let's just round that off. About 90 degrees. Okay, now we're going to kind of transition into a few of the triangle problems here. Okay, so we're going to solve a right triangle. So one of the things I wanted to kind of go through on that is just a few of the examples of triangles. I'm just going to draw out a triangle of some sort here. And just so that we can represent the sides correctly, mainly. It doesn't really matter how you draw that triangle. The key thing when you're drawing one of these triangles on this is that you use the correct naming convention. So you want to be sure that you do that. All right, so let's go ahead and label on this triangle what we're given. So basically the thing we always do is we always label this angle. I'm going to use what our textbook tends to do. Our textbook tends to be partial to Greek letters for angle. So that's gamma. We always use gamma to represent that. And then the side opposite that is C. And then these other two angles are interchangeable. If you call that one alpha, then the side opposite's A. And if you call this one beta, the side opposite is B, like that. Okay? So now we need to figure out what we need to find. Well, the things, I'm going to go around and just highlight what we need to find. Okay? Basically, I gave you A, so we need to find C, we need to find alpha, and we need to find beta. Okay, I always tell students to draw this and only try to use what you are given in the problem. So we were given beta, or side B, and we were given side A, like that. Okay, so now we're going to go through and solve the right triangle then by doing these things. Okay, so to begin with, we use the Pythagorean Theorem. C squared equals a squared plus b squared. Okay, it means the square of the hypotenuse is the sum of the squares of the legs. Okay, so we are going to square your legs. That sounds kind of funny. Okay, so take 3.2 squared for A, take 1.1 squared for B, and see, I just try to get the calculator to do this in one step. So I'm just going to go 3.2 to the second plus 1.1 to the second. Get the calculator to take over for you, and let's write down what we have. So that looks like that is 11.45. Now what I want to do is I want to take the square root of both sides. Okay, and when we do that, we'll get approximately what the answer to C is then, and then that will give us our first answer of the problem. So we just go square root of, square root of 11.45, and that's going to give about let's just round to say 1 decimal. Let's just say 3.4 is what that will be then. Okay, so we got that side, so we're done with that. Okay, now the next thing you got to do is pick an angle that you want to find. So let's just totally focus in on this A. And you got to talk out what I gave you. Okay, so I gave you, in relation to A side opposite, and I gave you a side adjacent. So that's what the definition of the tangent is. So what you would say is the tangent of alpha equals the length of the side opposite, 3.2, divided by the adjacent side, so you have that. Right? Now go to your calculator. Let your calculator immediately do this all for you. If you're finding an angle, you have to work out the inverse tangent. Okay, so what we're going to do is going to do this on the calculator. So I just go second tangent, 3.2, divide by 1.1, like that, and then that'll give me what alpha is. So alpha will round, let's just round to 71 degrees. That'll take care of that. So that's answer number 2. Right, so we're done with C. We found that. We found alpha. Now we find beta. So the key thing is alpha and beta add up to 90 degrees in a right triangle. So beta is just going to be 90 degrees minus the 71 degrees. So that's going to be 19. So the problem is solved. Okay, now one thing I want to show you guys on this, and I find this to be a real helpful thing to show students at this stage in the class. C is 3.4, so I have that. I'm going to just kind of box in all my sides. I gave you 2 sides. Now we know all 3 of the sides. I gave you a 90-degree angle. Now we know that alpha is 71, and we know that beta is 19. Okay. Now I can't really explain why this is, but you can check this way. So you can just basically pick a side. 3.4. Divide by the sine of the opposite angle. So the opposite angle is 90 degrees. So I can go sine of 90 and get an answer. Okay. Sine of 90 must be 1. Right? Okay. All right, now pick another side. How about 3.2? Divide by the sine of the opposite angle. The angle opposite that side is 71. Pretty groovy. It almost gives the same answer. Technically, it gives the precise answer if everything had infinite decimals in it. Then we got 1.1 divided by the sine of the opposite angle. Be sure you do the sine of the opposite angle. And it goes like that. So see, the thing is, you can use that to tell you're right. Okay, and it doesn't take very long to do that. And it would prepare you for something we do a little bit later in the semester. Okay, so that's how you check. All right, let's do one more illustration of a triangle problem. So again, this is a right triangle, so I'm just going to sketch out a right triangle. You can sketch it out however you want to, again, as long as you have the naming convention okay, then you're good. So let's label everything that we know, getting our angles labeled and everything correctly. So basically what we're going to have in here, if we go around here, again, the right angle is going to be gamma. The side opposite is C. Let's do it different this way, just for variety. That's alpha, that's beta, doesn't matter. So that means this would be A, and the side opposite, beta, would be B. So that's what we have. Okay, now this time in this problem, what we have is we have beta is 40.8 degrees. And we also have that side A is 2.9. So those are the two parts of this triangle we have. So I'm going to kind of box those in, and then we're going to use trigonometry to find the rest. Okay, so what that means that we need to find is we need to find alpha, side C, side B. We already know gamma is a 90-degree angle. All right, so you got to start somewhere. You got to start with an angle, basically, on this one. So the idea with this one's going to be, you actually don't have to start with an angle. That's just the way I'm going to do that. So we know that alpha and beta add up to 90 degrees, so I can just go 90 minus 40.8. Okay, so let's do it on a calculator. Be lazy. 90 minus 40.8 is going to give 49.2 degrees. Okay, so that'll take care of that piece. Okay, so we got our angle. Now we need to focus on finding the sides. Okay, so when we find a side, well, it's up to you where we start. I think I'm just going to start with B. Okay, and I'm going to talk out again what we have on this. So let's do this. So let's go, if we look at the angle I gave you, if you look at the side, and B, match up your ratio. Okay, look at this. This is the side opposite over adjacent, so it's the tangent again. Okay, it's not always the tangent. It always depends on what you're given. So we'd say tangent of 40.8 degrees equals the length of the side opposite over the length of the side adjacent, which is 2.9. And then we can solve this equation. Now this equation can be cross-multiplied if you want to. So B times 1 is B, and then you're going to go 2.9 multiplied by the tangent of 40.8 degrees, and then we can get an approximate answer on that. You want to make sure, of course, calculator's in degree mode. So let's see, go 2.9 times the tangent of 40.8 degrees. And that side is going to be now 2.5. Okay, so beta is 2.5, so now we got that piece. So we're done. Okay, so we got an angle. Now got a side B. Okay, so we got that step done. All right, so I'll kind of keep track of this as we go. Alpha, 49.2. B is 2.5. Okay, so that leaves us to find one more part of the triangle. So what we need to do on this is find C. Now you could do C with Pythagorean Theorem again if you want to. So let's just do that. So C squared equals A squared plus B squared. Okay, so that means C squared is equal to A. A was given as 2.9 squared. B we found to be 2.5. Okay, so we can just do this in a couple steps on the calculator. So what I'm going to do is 2.9 to the second plus 2.5 to the second. Okay, and that will give about 14.66. Now I can square root both sides, and that'll give the approximate answer to C. Okay, so that is about 3.8. So now we have got our answers to these problems. Okay, triangle solved. Voila. Okay, you could do the same checking mechanism I did on the last problem if you wanted to. All right. So next thing we're going to do is a couple of applications, and just a few more things to finish this up. So these kind of things you always got to draw a diagram on. The biggest challenge students tend to have on these problems is drawing the diagram correctly. So I want to be kind of careful about how this goes. All right, and I'll just do the best I can. It isn't going to be a very good diagram, but you'll get the idea. So looks like we have a boat that's on a lake, and then there's a cliff. So let's kind of call this is my cliff. And then you got you got your lake. That's your lake. Lots of waves. It's a windy day. Here's your boat. It's a pretty sailboat. And let's see. It says the angle of elevation to the top of the cliff is 30 degrees 56 minutes. Now we make an assumption. We are kind of thinking like the cliff is at a right angle. It's a perfectly straight line. There's no waves on the lake. It's a perfectly calm day. And this guy's measuring the angle of elevation perfectly from the level of the water. Of course, that's a bunch of BS, isn't it? But what we do a lot of times in math is we go through and we kind of make approximations. Okay, so we got that. All right, so it says from the boat on the lake, let's see, we got 30-degree angle of elevation. All right, so that's 30 degrees, 56 minutes. Angle of elevation means you're looking up at something, okay? Then it says the base of the cliff is 127 feet from the boat. Then we're going to find how high the cliff is. So we're going to end up basically doing these two things. So we're going to end up having, okay, this side right here is 127 feet from the boat, the base of the cliff is. And then this is going to be the unknown, the height of the cliff. So if you talk out what you have, which is always the key when you're setting these things up, you have this angle. This is in relation, a side opposite. That's a side adjacent. It's tangent time again. It isn't always tangent time. It just has kind of worked out that way on this. I didn't really mean that. Okay, so let's get everything set up then. All right, so what we're going to do is we're going to say the tangent of the angle, 30 degrees 56 minutes, is equal to the side opposite, x, over the side adjacent, 127 feet. What you're going to do is cross multiply this. So you're going to have x equals 127 tangent of 30 degrees 56 minutes. Go to the calculator, and we got an outstanding answer here. All right, so 127 multiplied by the tangent of 30 degrees 56 minutes. So I'm going to put it in like this. Okay, get the answer and round that off, so that will be about 76.1 feet, would be approximately how tall that cliff is. Okay, so that's a correct answer. Let's move on to the next one. And again, let's try to draw a picture. So it looks like we have a balloon. So I'm going to draw a picture of a balloon. Okay, here's my balloon. It's got like a pie on it. It's a math balloon. Okay, and let's see. It says the balloon, from the balloon, that's 1,024 feet high. We're looking at an angle of depression from the boat now. Okay, so first of all, if you were to go down, it looks like this is, I'm going to write that. That's going to be a side of your triangle, so it looks like that's 1,024 feet high. Now we're looking down at something, so this would be like the ranger headquarters is down on the ground somewhere. And angle of depression means you're looking down at something. So this would be like this. So if you were to look at, if you were looking straight parallel to the ground, and then if you're looking down at something, that formulates what we call the angle of depression. So this angle of depression is that angle of 88 degrees 17 minutes. Now obviously I didn't draw that to scale, but it doesn't matter. So if your angle of depression is that big, you're just like almost right on top of what you're looking at. So what we need to do on this is it says how far is the headquarters from the point directly below the balloon. So here's the headquarters, there's the point below the balloon. So that's what we're trying to find. Well, the first thing that you got to know is when you have two parallel lines, these angles right here are congruent. Those are called alternate interior angles. So now if we talk this out, and it looks like we got tangent time again. Gosh, I should have given more variety on this. And tangent works out a lot. A lot of times it's just kind of works out that way. So we're going to look at this angle. We're going to look at this and this. So if you talk it out, again, what you have is you have a side opposite, you have a side adjacent. So to solve the problem, you would say tangent of the angle, 88 degrees, 17 minutes, is equal to side opposite, 1024 divided by x. Okay, so what we'd have to do is we'd have to cross multiply this. So if we cross multiply it, we'd have x times the tangent of 88 degrees, 17 minutes, equals 1024. Then we'd have to divide both sides by this. So we'd have to go like, okay, let's divide both sides of this equation by tangent 88 degrees, 17 minutes. So we want to do that. And then we can go to the calculator. Okay, so let's go ahead and do this. Okay, so we got 1024 divided by the tangent of 88 plus 17 parts out of 60. I just like to keep doing it that way. And then we can round that off, so that is about 30.7 feet. Should be the solution of that problem, okay? Number 26. Let me check on my answer key real quick on that and make sure I got that okay. Look at that. I got it right. Yes. The teacher knows what he's doing. He's waking up. All right, one more problem, and we will wrap it up, okay? All right. Hey, Colorado problem. It's a ski resort. Yeah, so it says the chairlift at a ski resort has a vertical rise of 3,900 feet. The length of the ride is 1.2 miles. What's the average angle of elevation of the lift? Okay, I kind of look at this way. Well, okay, I guess what you kind of have, well, you got your mountain. Okay, you're heading up to this point here, kind of like this. Then you got this ski lift that's kind of doing something like this. So this is the way I interpret this, and we'll see if I'm right. So we're going to assume that this maybe is a hypotenuse of a right triangle. So that's your ski lift like that. And let's see. We're going to kind of make a triangle kind of going through like this, kind of considering that you're inside of the mountain. Then it says it has a vertical rise. So that's going to be talking about this piece right here. So that looks like that's 3,900 feet. Okay. And it says the length of the ride is 1.2 miles. So that length of the ride has to be that hypotenuse of the triangle. Now what you're going to do is find the average angle of elevation. Okay? All right, we have something different than the tangent for a change. Awesome. Okay? So here's what we have. We have an angle. We have a side opposite. And we have a hypotenuse. No longer tangent time. It is sine time. All right, sine, everywhere a sine. So we have sine alpha equals side opposite, 3,900, over hypotenuse, 1.2. Now what we have to do on this is we have to do an inverse sine. So we're going to say alpha is going to be equal to the inverse sine of 3,900 over 1.2. Okay, like that. So we just do this on the calculator. We'll say inverse sine, 3,900 divided by 1.2, and that's going to be an error. That's a good way to end this lesson. So what did I do wrong? Oh, okay. All right, here's the deal. Okay, so, okay. All right. Got to finish this great lecture off with one more great mistake. Okay, and that's fine. I mean, look what I wasn't paying attention to. Seriously, look at this. That's feet. That's miles. Okay, units got to be consistent because things just don't work out if they aren't the same. So you need to take your pick on which one you want to change. I think what I'm going to do is I'm going to go ahead and we're going to do this. All right. In fact, I'm just going to clean that up and pretend like I didn't make that mistake. You can do the same. All right, so let's go through and do a conversion on this, then we're going to get a good answer. Okay, the reason I was getting an error on the calculator is because it was doing an inverse sine of a number that was bigger than 1. So what I'm going to do is let's do a unit conversion. It does not matter which one you do. You can take feet to miles or miles to feet. So let's take 1.2 miles and let's multiply that out and convert that to feet. Okay, so we know that in 1 mile, and hey, we're all people who live in Colorado, we know that Denver is the mile-high city, so it's 5,280 feet, like that. Miles cross out, and then that will give the length of that side then. So let's do that now. We got 1.2 times 5,280 is going to be equal to this. That will be 6,336 feet, like that. All right, so this thing right there gets changed to 6,336 feet. Now everything's consistent, so we're good. So what we're going to do is the sine of alpha is equal to the side opposite, which is 3,900 feet, divided by the hypotenuse, 6,336 feet. Now see, this ratio right here is less than 1. You can only take the inverse sine of a number that's less than 1. So what I'm going to do then on the calculator, you'll see that I'll get an outstanding answer now. So inverse sine, 3,900 divided by 6,336. Now I should get a good answer. There we go. So much better. All right, so we got alpha equals about 38 degrees. Problem solved. Okay, watch out for those units. Teacher can be sneaky sometimes. Am I right? Oh, look at that. It's a thing of beauty. All right. Okay, so that will wrap this up, and this will kind of give you an idea of what you need to be able to do with the assistance of your calculator on this exam. Good luck to you.